Hi everybody, my name is Miro. I'm the author of Titanoboa, which is a distributed workflow orchestration platform written in Clojure. I'll be talking a little bit about distributed systems and microservices. Super excited to be here. Today, albeit virtually. So let's get started. Let's start with something fun. So let's pretend for a little bit that instead of software engineers, we are spaceship engineers, and we are actually in charge of some space travel. So let's maybe pretend that our goal today is to take astronaut instead of some program and deploy to some planet. So instead of a server. So usually we would deploy astronauts to planet using some spaceships, and once they get there, we would just broadcast to them some transmission via radio, maybe give them instructions. But here's the thing about space. It's an inhospitable place. Many things can go wrong, right? Spaceships can fail. They can hit objects maybe in space. You need to configure them. You need to maintain them. It's not an easy task. If you receive some distress signal from some derelict ship and you go investigate, we all know how it ends up. But we are smart people. We are smart engineers. And we've been asked by this astronaut, so that will be our program. Let's call her Ellen. Ellen wants us to help with the space travel because it's hard. She has her small spaceship. It might be called, I don't know, Node.js or Jelly or something like that. And you can see straight away, this is not an elegant solution, is it? But we are very smart engineers, and we sit, and think long and hard about this problem, and we come up with this brilliant solution. So we just built a bigger ship, and we put the original spaceship in it, right? And if you step outside and look from the outside, and basically the original spaceship disappeared. You no longer need to maintain it or configure it. It's been taken care of, right? So everybody is happy. There still might be few naysayers and glass half empty type of people who complain that they don't have much visibility into where they are flying to, or they can't steer properly. So we just built more spaceships. We call them sidecars and attach them to the container ship. Right, but then you have all these spaceship factories on Earth. It's still not elegant. Maybe if you want to really scale and maybe colonize the whole universe, we can still build even bigger spaceships, and we can put the spaceship factories in them and maybe ship it to the edge of solar system. And pretty much if you are on Earth, it's been taken care of. There are no factories, there are no spaceships. It's basically all automated, right? You still may need to train the astronauts, get them to the space station, put them in ships, then to container ships, and then tell them where to fly to. But apart from that, it's solved problem. But here's the thing: what if maybe we've been focusing on the wrong problem? Like, these ships are certainly technological marvels, and it's fun to play with them, but maybe we've just become too attached to them. So what, maybe with space exploration and travel, maybe this would be one possible approach. Maybe this would help us. So maybe teleports would be a good thing, right? What if we just needed in some cases teleports, and we've just been given more and more spaceships? So let's step back and let's look at this analogy from the IT perspective. So what does it mean, teleports versus spaceships? Well, here on the left hand side, basically this is the traditional approach we usually take when we build distributed systems and we deploy microservices, right? So you write some program, you put it into some server, like web application server. It could be like Jelly or Node.js or something, and then you basically deploy it into some container and put it on server, right? And then this would be some usually program written in something, usually some object-oriented program. It maintains its state, especially when running in the web server. You communicate with it via some imperative API you predefine, like either via REST or gRPC. It's pretty much the same, and it's bound to one address space. On the other hand, if you just build programs that are distributed in nature, you don't ship the whole system, you don't ship the whole web server. You just write a program that depicts the logic you need to execute, and then you have it somehow serialized and sent over to the servers where you need it executed. So you just send the whole logic, and by nature the program maintains its own state even though it's crossing boundaries between servers. And for this approach, usually what's more suitable than OOP, it will be the functional programming paradigm or the data flow programming paradigm. And pretty much your API that you are using is the programming language, right? So you have declarative, pretty much Turing complete API that you can invoke, and you focus more on the workflow, so end-to-end what you need to perform. You are not just thinking in terms of each particle atomic operation, like when it like in case of microservices. So you define the workflow. You can call it abstract syntax tree or directed acyclical graph, or you can have some DSL, and with that you define what needs to be executed. So this is usually address space agnostic, right? You might have some security concerns, like what happens if somebody breaches the teleport, like if some alien life form gets there. It might be more concerning than if in traditional approach somebody breaches this planet, then it's pretty much enclosed system, right? So that there are certain upsides and downsides to this. So let's have a look at the history. Like, do we have teleports? Do we have this approach? Of course we do. Of course we've been using it, and pretty much everybody's been using it, maybe even without knowing. So there's a whole paradigm called data flow programming, which basically models the programs as some directed graphs, and these graphs then can be distributed across network and clustered of computers, and basically that kind of makes of network transparent distributed programming model. So there are many very interesting papers in this regard. I'm just listing here a few. Notable work by Bob Sutherland, pretty much a pioneering work in terms of like specifying first graphical representation of a programs that can then be distributed across computers. Ostrovsky's work is also quite notable. Main point here in his notion of what he calls live distributed objects is that programs pretty much can be orthogonal to the underlying infrastructure and the underlying runtime. And there are, of course, multiple languages already that kind of implement this distributed programming approach. So there are languages that by nature are distributed. I'm listing here a few, like Hume, it's a Haskell-like distributed programming language, Cuneiform, which is basically written in Erlang, and many others. But these are pretty niche. Usually use them, to process some data. But in in your favorite programming languages or in mainstream programming languages, usually if you build distributed systems, you just build it using the distributed protocol. So you either make some REST calls behind the scenes, or you use some RPC. A couple of decades ago, Corba was big hit. These days, gRPC, it's pretty cool, but it's quite the same. You have IDL, which is interface definition language, and you define the interface in it, and then you can make calls, and even though it crosses network and goes over to some different address space, it feels like you are actually invoking your own code. We have RMI in Java land. It's been around. It's pretty good. Making note here of Apache Spark. You would think Spark is written in Scala. It runs on JVM, so you would think it uses RMI, but when you invoke Spark context, then it sends data for processing to other servers. But in reality, if you look at Apache Spark's code base, you would see that it just takes the functions and methods you want to invoke, and it serializes them and invokes them on the other end. So this is, in some circles probably this would be considered a heresy, but still it's a part of mainstream technology everybody's been using, and it pretty much resonates and corresponds with the data flow programming approach. So let's jump into REPL and let's have some fun with programming and with Clojure. Programming is Clojure is very suitable for building distributed systems because simply it's functional language, and also we have the sense of homoiconicity, which means that the program is also the same as the data, and vice versa. So I have here two REPLs. These are separate REPLs. As far as we are concerned, this could be running on separate servers. And I will make use of the core async concept. So I will define some channels. So let me define this channel mychan in one and again in the other. But this is not ordinary async channel which would work only on one machine. This is a distributed type, and if it's basically I'm using libraries from titanoboa which rely on some underlying message queue, and if I here send into the new channel, I send this map with this message. I'm using the core async command or function for putting the message on queue. So I send it here in this REPL, and in the other one I can consume it. So here you can see, even though we are in different address space, we got the message, but this is nothing ordinary, extraordinary. It's pretty common, right, using some messaging systems. But what we can do next is that here we define another channel. We call it response channel. Maybe we'll use it for getting responses from the other server. And then we can also define more complex message. So now to this channel we'll send a map with these key value pairs. So we'll have some message here, and we will send also not only data, but we'll send some instructions. So we have here anonymous function that we'll send over. We'll provide input for that function, and here's the response channel where the other side should respond once they invoke the function with the parameters, and they should return us the result. So this pretty much feels like teleporting and teleport, right? We created a new queue and we are sending it over the wire to some other system. So let's consume the message here. So we have the message. We can even check how the message looks, and you can see we got it, right? And now we can execute the function we've been given and return back. So here we'll respond to the response channel, so resp_chan, and we'll send back the original message just to for sake of consistency, and we'll attach this key result with the value, basically taking the function we've been given and applying it to the input, right? And here we can check whether we've got it and whether, yeah. So here's the result. It's very simple, hello world, but we basically accomplished it, spanning multiple address spaces. So that's interesting, and I can jump, very quickly back into the presentation. So basically, this very approach I'm using in titanoboa, it just does the same thing. It just serializes the work as some graph. So you can define some workflow that you need to execute. It's basically a graph, and this way we can distribute it over many nodes, and it makes for quite a flexible type of workflow system. So maybe let's play with it a little bit more. So here I have the titanoboa running in AWS, and I have some workflows here. So just similar type of hello world workflow. Basically here I have some hello world. It's slightly more complex, but not that much. It takes a parameter name, it creates a PDF using this function, it prints some hello world in it, and it then uploads it to S3, and then it will send me a Slack message sending link to that particular PDF. So I can invoke it. Either I can invoke it from here, I can even send a request from Postman. So I can say here maybe and if I send it, I'm gonna, yeah, and here I got the Slack message, and I can open it, and you can see we got the hello world message, right? So that's pretty cool, I think, but it's not the main thing I wanted to talk about today. So let's have some fun with data. I have here some data files that need processing. In 2020, for some reason, a lot of genomic sequencing data became publicly available on the internet. I have no idea why is that, but let's have some fun with that. So I have here some FASTQ files. These are basically files from genomic sequencing, and these files are just textual files. So if you are not familiar with bioinformatics, just don't be scared. These are just, strings. Basically, these are files full of strings. These are the nucleotides, the 4 nucleotide bases. So each letter represents either adenine, cytosine, guanine, or thymine. And basically, you can just see here all these strings. And we will do today some very simple exercise, which is called K-mer count. It's counting the substrings. So I can say, I need to count substrings of 3. So this would be 3 mers, or substrings of 4. This would be 4 mers. And basically, this is one 3 mer, this is another one, this is another one. And this counting of K-mers can become CPU heavy operation. It can require some memory. So it's not a simple exercise, even though it's not that hard. So we can create some workflow to process this file and to create a K-mer count. So I will create a workflow here. I'm gonna call it K-mer count. Now it's not that hard. We could implement this functionality probably in a few minutes, but to save time, I already have it here. So I already created. So here's the code. Basically, there's one function to count the K-mers, and I may need to do some parallelism. So I have some function to split the processing. And what I need, because it's I have this in Maven repo, so because I haven't worked with it, I may need to import this dependency, right? So I take this dependency. I already, I think, included it here. Yeah, so I already do have it, but if I didn't, I would just copy paste it here and save it, and it would get automatically updated on the server side. So I have the dependency here, and I can just so I have autocomplete here, so we can K-mer, and then this would be the K-mer count, and here I'm also having some sample property. So we would be invoking this function, and I would need these properties. So you can see again we are just creating some graph. So this is this is just some map with some values in it that defines the workflow. It's nothing else. And we can, so here I have the file, we can use that. I can save it. Also, I have REPL here, so we can even evaluate it. Basically, the properties I defined here are automatically accessible using this value. So if I just hit Control Enter, I can see the values, and in the same fashion, basically, here I can just see from the file, the first, I think, from first 12 lines, these are the top K-mers. So it worked, just validating this variable, but the file is huge, and I may need some parallelism, right? So I need to add another workflow. And again, we don't have that much time, so I predefined the workflow here. So it's again just data, just graph, and I can update it here. So this will run over the file. It will split it in multiple parts and then invoke the K-mer count workflow on each part, and each of these K-mer counts will return top n. So here's top 10 frequencies from the K-mer count. So it will count the substrings and return us the results. But here's the thing: we have few minutes. This will run on this particle file. It's huge. It would run like 20 minutes. So what shall we do? Should I panic? Should I call organizers? We need more time. Well, I have here this workflow, which is called add nodes, and what it does again is just another, it's just another graph, and I can just invoke this and say how many instances I need to add to this cluster, and it's going to be added. So far this has been just one CPU T2 micro instance, so it's pretty tiny. So I'm going to add more now, so we'll add 20 nodes to the cluster. Again, I'm adding just two T2 micro instances, so please don't tell anyone in the data science community because they would bash me for that. I should probably use C5 or some large servers for that, but this is just a demo, and you can see already some nodes are coming up. So, and we have 21, so it's 20 plus 1, so we got them all. If you don't know why is that they came up so quickly, maybe there's a thing or two you need to learn about cloud computing. Everybody complains about JVM startup time and everything, but still there are ways how to approach this issue. So that was that. We can see on here the job for adding nodes completed. We have the instance IDs here. So let's start K-mer map reduce, and we'll split into 20 parts. And we are running. So just to summarize, while we are waiting for this to finish, what we've just seen, we basically taken some A1 dependency. So it was just some code, right? We deployed it into our server, so that leveraged the ability of JVM to just load classes during runtime, and without any type of packaging. We didn't have to compile the code, we didn't have to build any Docker images, we didn't have to deploy them into repository, we didn't have to update any Zookeeper servers, we didn't have to update our cluster and restart some master node, right? It pretty much smoothly ran during runtime, and you can see this is running. It's basically processing the file, it's splitting it, and we might need to wait a little bit more. We should see CPU slowly picking up at some stage when the counting starts. Yeah, and now we should see the splitting finished, right? So now we have multiple jobs that are running. We have 20 jobs that are running in parallel and counting the occurrences. And now we just wait. So while we wait, I know very good distributed systems joke. I might tell you to spend the time, but I'm not sure it would get to everybody in the audience here, so I might not tell it. And we can see already the jobs, some of the jobs are finishing so slowly, but it's not it's not taking 20 minutes as it would if we were running we should see already, you know, the CPU load in the cluster is picking up, which means the nodes are actually doing something. So some of the nodes you can see are working hard. And if I open one of the jobs, we should see in properties the counts of K-mer. So each of these workloads will finish with some portion of the file, so it will basically count these lines from the start to end in the FastQ file. And here are the counts. And the reduce function here will basically merge all these together and adds everything all together, right? And we finished. So pretty much here's the final job. And ladies and gentlemen, I give you here the final K-mer counts for this particle large file. So that's it. We managed in time, I think. So thank you very much. I'm looking forward to Q&A session coming up. And if you would excuse me now, I'm going to stop all these instances just to save some money on my AWS bill.